So now we are going to see uses of dimensional analysis. So there are three uses of dimensional analysis. First is to check the correctness of physical equation. Second is to establish the relationship between related physical quantities, and third is to find the conversion factor between the units of the same physical quantity into different systems of units. So now first we are going to see to check the correctness of physical equation. That is, the dimension analysis used to check the correctness of physical equation. So in which in any equations relating different physical quantities, if the dimensions of all the terms on both the sides are the same, then that equation is said to be dimensionally correct, and this is called the principle of homogeneity of dimensions. So for this we consider first a equation of motion. V is equal to u plus at. So for this equation you have no both equation, any equations have two sides, left side and right side, and if the dimension formula for all the terms same, then this equation is dimensionally correct. So dimensions of LHS, that is, here is a LHS is a v, dimensions of v, that is a velocity, dimensions of velocity you have no L t raised to minus 1. Then so suppose this is the final velocity, u is the initial velocity, and its are the L t raised to minus 1, t raised to minus 1. So actually L raised to 1, L raised to 1, m raised to 0, because there is no mass, m raised to 0, and also at, at is acceleration into time. So you have no the uh, acceleration dimensions, m raised to 0, L raised to 1, t raised to minus 2, and time m raised to 0, L raised to 0, and t raised to 1. So it is equal to at is equal to m raised to 0, L raised to 1, and minus 2 and plus 1, that is t raised to minus 1, t raised to minus 1. So v velocity dimension formula, m raised to 0, a raised to 1, t raised to minus 1. For initial velocity, m raised to, for this m raised to 0, a raised to 1, t raised to minus 1, same. And for this term 80, m raised to 0, l raised to 1, t raised to minus 1. So for all this term dimensional formula is same, therefore this equation is dimensionally correct equation. Also we can see AC is equal to 80 plus 1 upon 2 80 square. AC is equal to 80 plus 1 upon 2 80 square. 1 upon 2 80 square. This is UT. UT AC is equal to UT plus 1 upon 2 80 square. You can also find out this equation is dimensionally correct or not correct. So for this AC is equal, AC is a displacement, and which is equal to dimension formula, AC is a displacement, is a length, m raised to 0, t raised to 0. Then for UT it is a velocity, initial velocity is velocity of m L raised to 1, m raised to 0, t raised to minus 1, and here is a t raised to minus 1. So UT is equal to what? L raised to 1, m raised to 0, t raised to minus 1, and minus 1, t raised to is a minus 1, it is a t raised to 1, not a plus, it is only plus, it is t raised to plus 1. So minus 1 plus 1 0, so t raised to 0. Then for 80 square, it is acceleration. Acceleration is formula for dimension formula for acceleration is L raised to 1 m raised to 0 t raised to minus 2, and for time here is a square, therefore t raised to 2. So 80 square is equal to L raised to 1 m raised to 0 minus 2 and plus 2 t raised to 0. So for s term, L raised to 1 m raised to 0 t raised to 0 ut L raised to 1 m raised to 0 t raised to 0, and 80 square L raised to 1 m raised to 0 t raised to 0, all terms having the same dimension formula. So therefore this equation is dimensionally correct equation.